Welcome to a review video for electrostatics. Before we begin, this topic is one with multiple formulas and concepts, so you'll need to understand for the final. So let's begin. First, the basics. You will need to understand the atom. The atom is made up of three components: protons, neutrons, and electrons. Protons are positively charged molecules. Neutrons are neutrally charged, meaning they don't have a particular negative or positive charge. It's neutral. Electrons are negatively charged and determine the characteristics of an element or molecule. Protons and neutrons are placed in the nucleus, whereas electrons orbit the nucleus. So what is an electroscope? An electroscope is a device that is most commonly used as a charge detecting device. In class, we did an extensive lab on the electroscope and how it works, so if you feel the need to review this topic further in detail, we recommend you to either look at your lab packet or access it on the classroom website. In this example, the electroscope is approached by a negatively charged rod, and because like charges repel, the negatively charged electrons move farther down the electroscope and the leaves repel. The next case is the exact opposite, and the leaves repel because of the positively charged leaves. Okay, now let's move on to charging methods. In this review video, we'll cover charging by induction, conduction, friction, and polarizing. In the induction process, a charged object is brought near but not touched to a neutral conducting object. The presence of a charged object near a neutral conductor will force or induce electrons within the conductor to move. As you see in diagram 1, a metal sphere with an excess of negative charge is brought near to a neutral electroscope. Upon contact, in diagram 2, electrons move from the sphere to the electroscope and spread about uniformly. And in diagram 3, the metal sphere now has less excess negative charge, and the electroscope now has a negative charge when it moves away from the electroscope. Okay, now moving on to the next first sample problem. In this problem, it states, number 1, a neutral metal sphere is touched by a negatively charged metal rod. As a result, the sphere will be blank and the metal rod will be blank. Select the two answers in their respective order. Number A, positively charged; B, negatively charged; C, neutral; D, much more mass; E, not enough information to tell. The answer is B. In this case, of charging by conduction, when a charged object is used to charge a neutral object by conduction, the previously neutral object acquires the same type of charge as a charged object. The charged object maintains the same type of charge that it had originally had. So in this case, both objects have a negative charge, which is answer B.
This is an example of charging by friction. Two balloons rubbed on human hair will become negatively charged and have an attractive interaction with the hair. If the hair is removed, the balloons repel. Charging by friction is a process of transferring electrons between two objects that are rubbed together. In addition, conductors cannot be easily charged by friction, as the extra electrons gained can easily escape. This is sample 1. During a physics lab, a plastic strip was rubbed with a cotton and became positively charged. The correct explanation for why the plastic strip became positively charged is that A, the plastic strip acquired extra protons from the cotton; B, the plastic strip acquired extra protons during the charging process; C, the protons were created as the result of the charging process; and D, the plastic strip lost electrons to the cotton during the charging process. When two different materials are rubbed together, there's a transfer of electrons from one material to the other material. This causes one object to become positively charged, less electrons, and the other object to become negatively charged, or more protons. Therefore, the answer to this question is D. This is an example of polarization. A stream of water falling vertically can be deflected by the presence of a charged object. In this example, the charged object is a negatively charged balloon, which is deflecting the positively charged water molecules, showing that the water molecules are polar and can align themselves to be attracted to charged objects. This is the sample problem for polarization. Charged rubber rods are placed near a neutral conducting sphere. causing the redistribution of charge on the sphere. Which of the diagrams below depict the proper distribution of charge on the spheres? List all that apply. Diagram E shows a metal sphere with an overall positive charge. This should never happen because you can never get rid of all of a single charge in a sphere to either make it completely positive or completely negative, just through polarization. Diagrams B and C show that the charge on the rubber rod are attracting like charges, which also does not happen to be true due to Coulomb's law. Diagrams A and D properly show the charge distribution, with the charge on the rod attracting the opposite type of charge while still showing a representation of the other charge in the sphere. Now, this is Coulomb's law, which is probably the most important law in electrostatics. Coulomb's law states that the magnitude of electrostatic force of attraction or repulsion between 2 point charges is directly proportional to the product of the magnitude of a charge and inversely proportional to the square of the distance between them. So in short, like charges repel, opposite charges attract. And the equation for Coulomb's law, where F is electrostatic force, K is Coulomb's constant, which is 9 times 10 to the 9th newtons. Q1 is charge on object 1, Q2 is the charge on object 2, and R is the distance between the charges. This is sample problem 1 for Coulomb's law. Suppose that 2 point charges, each with a charge of 1 coulomb, are separated by positive 1 coulombs are separated by a distance of 1 meter. Determine the magnitude of electric force of repulsion between them. You are given Q1, which is positive 1 coulomb, Q2, which is positive 1 coulomb, and the distance, which is 1 meter. Once you plug all that into the equation, you get the electric force equals 9 times 10 to the 9th newtons. Sample problem 2 is 2 balloons with charges of positive 3.37 microcoulombs and negative 2.1 microcoulombs attract each other with a force of 0.0626 newtons. Determine the separation distance between the 2 balloons. You are given positive 3.37 microcoulombs, which is positive 3.37 times 10 to the negative 6 coulombs, and negative 8.21 microcoulombs, which is negative 8.21 times 10 to the negative 6 coulombs, and the electric force, which is negative 0.0626 newtons. Then you plug it all into the equation. After rearranging the equation to get the distance, you get the distance equals positive 1.99 meters. Electric force. Electric force is a force that pushes apart 2 like charges or pulls together 2 like charges. The equation is the same as Coulomb's law. Sample problem 1. A positively charged object with a charge of positive 85 nanocoulombs is being used to balance the downward force of gravity on a 1.8 gram balloon that has a charge of negative 63 nanocoulombs. How high above the balloon must the object be held in order to balance the balloon? You're given the charge of the 2 charges, and the distance in meters can be found using the same formula as Coulomb's formula. Electric field. Formula for electric field is Coulomb's constant times charge over distance squared. This is a vector quantity. This measures the potential force of a given spot in a space by the electric field. The greater the density of the lines, the stronger the electric field, as shown in the example below. In sample problem 1, consider the electric field lines shown in the diagram below. From the diagram, it is apparent that object A is either positive or negative, or object B is either positive or negative. The answer is D. Electric field lines are directed towards object A, so object A must be negative. They are directed away from object B, so object B must be positive. Sample problem 2. What is the strength and direction of the electric field 3.37 0.74 centimeters on the left-hand side of a 9.1 microcoulomb negative charge. Given is the coulomb's constant, distance, and charge. And to find the energy, you have to use the electric field formula, which is coulomb's constant times charge over distance squared. Once you plug it in, you will get 5.8 times 10 to the 7th newtons per coulomb.
So now we're talking about electric potential energy. The formula for electric potential energy for point charges is the electric potential energy equals constant times source charge times charge of the object over the distance between the two objects. Electric potential energy is a scalar quantity, so that means direction does not matter. The uniform field formula for electric potential energy is UE equals negative K Q over R. This measures the amount of potential energy based on the distance between the two charges, or between a charge and an electric field. Here is a picture. So, here is a sample problem. Please read the sample problem and pause the video to try this problem on your own. Okay, so here's the solution. We use the formula for the electric potential energy, U equals K Q1 times Q2 over R, and then we plug in the variables, and then we get the answer 4.62 times 10 to the negative 28th joule. Here's sample problem number 2. Please read the question and attempt to answer the problem on your own, and don't forget to pause the video. Here's the solution. In order to solve this problem, we split the problem into x and y direction. We use the formula for electric field, E equals kq over r squared, and then to calculate the electric field in the x direction, we plug in the variable and we get 900 newtons per coulomb. And then we find the electric field in the y direction, which is also 900 newtons per coulomb. Then, to put everything together, we use Pythagorean theorem, and then we get 134 newtons per coulomb. After that, we use the inverse of tangent, which we get the direction of the electric field, which is 45 degrees north of east. Now we need to find the potential electric energy, and we use the formula U equals K times source charge times charge of the object over distance. And we know that in this scenario, Q1 equals the sum of the two electrons. So that's why we do 1.0 times 10 to the negative 6 coulomb times 2. And then we know that given the problem, Q2 equals another electron. So we multiply that first Q1 by Q2, which is 1.0 times 10 to the negative 6 coulomb, and divided all of that by the distance, which is 1 meter. And we get the potential energy as 1.8 times 10 to the negative 2 joules. So now we're talking about electric potential. Electric potential is the possible electric potential energy in a certain spot in an electric field. And something that's relative to electric potential is voltage. Voltage is the difference in potential energy per unit charge between two locations in an electric field. The formula for electric potential is V equals kq over r for the point charge, and for the uniform field, it's V equals negative electric field times R. By substituting E with the formula of uniform field for electric field, we get V equals kq over R. So here's a sample problem. Please do the problem and pause the video and attempt to solve the problem on your own. So here's the solution for the problem. We use the formula for the point charge, V equals kq over r. Then we plug in numbers and we get the electric potential equals 2.88 times 10 to the negative 11 joules per coulomb. So here's sample problem number 2. Please read the question carefully and pause the video to attempt this question on your own. So here's the solution. The answer to part A is 1 higher, because we assume that the points in space have a positive charge. And since similar charges repel each other, the closer the 2 points, the higher the potential. Thus, the point closer to the charge has a higher potential than the point that is further away. For part B, we use the equation V equals KQ over R. We substitute in the variable, and we get 1.2 times 10 to the 5th volts, or joules per coulomb. So now we're talking about principle of superposition. The principle of superposition allows for the combination of two or more electric force, charge, field, potential energy, and potential. The principle of superposition states that every charge in space creates an electric force, field, potential energy, and electric potential at point, independent of the presence of other charges in that medium. This allows students to solve for a problem where there are multiple charges. So, here is a practice problem. Please read the problem and pause the video to attempt to solve this problem on your own. So here's the solution. We're going to use the equation for electric field to solve this problem. First, find the electric field exerted on P by Q, negative Q, and the other P. Then, use the electric field's formula, KQ over R squared, to determine the force exerted by each of the charge. Since the 2 plus Q are equal distant from P, the force field in the y direction cancels out, leaving us with only the force in the x direction. And since negative 2Q is directly to the left of the point, there is no force in the y direction by that charge. So we just add the 3 electric field and determine the final direction and the strength. And we get the total electric field at point P is 1.44 newtons per coulomb, and the direction is to the left. Now here's sample problem number 2. First, we need to find the distance between the center of the square and the charges. And the distance is root 2, or around 0.707 meters. Then, we use the formula for the electric field to determine the electric field extended on the center of the field by the 3 charges. We have to split the problem into x and y direction using sine and cosine. And then, add the force field that is in the same axis. Finally, we use Pythagorean's theorem to determine the strength and direction of the electric force field at the center of the square. As an answer, we get 1.08 times 10 to the 5th newtons per coulomb, with a degree of 225. Thank you, and this is the end of the video.